Hi everyone, welcome back to the channel. In this video, we are going to see very innovative approach in computer vision, that is Convolutional Kolmogorov-Arnold Networks. This approach is based on the CAN architecture. If you remember, I have created one video on CAN approach, which is recent approach and can be seen as the alternative for the multi-layer perceptron neural networks. Before to study this architecture, we need to see some other architectures, such as first we will see deep neural network architecture, then convolutional layer from convolutional neural network architectures, then we will see CAN architecture, then finally we are going to see the convolutional CAN architecture. Also, we are going to implement this method using Google Colab. So let's start with the introduction to deep neural networks. So here my aim is to provide a fundamental understanding of deep neural networks for those who are unfamiliar with the concept. On the left part of the diagram, you see different types of networks that are known as general purpose utility networks for feature extraction, and these networks can be convolutional neural networks or recurrent neural network, long short-term memory, attention mechanism, pooling layer, etc. Whereas on the right side we see fully connected layer, we also call it as a dense layer, that are used for classification and regression tasks to solve any specific problems. Basically, the diagram shows how raw inputs are transformed through various layers to predict classes. In a way, it's a path from input to feature extraction and classification. So the next is a convolutional neural networks. We are not going to see each and everything, but just to give you idea, this is the diagram where you see first part is for features learning. The second half is a classification layer, which has a fully connected layers and output layer. Now we will see convolutional neural network, the components present in convolutional neural network. So the first is a input layer. It is the initial or first layer of the network that receives the input image data. Okay, and the second component of the element of this network is convolutional layer. It actually applies different or several filters to detect features such as edges, corners, etc. Then there is a pooling layer. It actually reduces the spatial size of the convolved features. In a way, it helps in reducing computational power, computational load, and also overfitting problem. Then comes in flattening layer. Flattening layer converts a pooled feature map from two-dimensional to one-dimensional array. It is a input for the fully connected layer. Then next part is a fully connected layer. It is also called as a dense layer, and it uses features to classify input data into several classes based on the training data sets. And the final layer is output layer, the output layer that gives the output or the prediction results. So for the purpose of this video, we are going to see convolutional layer in detail. So what are the different components we have in convolutional layer? In the first component is a filter, or we also call it the kernel feature detector. It's a small matrices used to extract features from images input layer. Okay, then feature map is a result matrix of applying the filter across the image. Then there is a stride concept. It is a number of pixels by which the filter is moved across the image. The fourth one is the padding. It actually adds the pixel around the image borders. And then there is also the concept like activation function. So typically for the convolutional layer, we use the ReLU, rectified linear unit activation function, which actually used to introduce nonlinear properties into the network. And here I provided some code snippet for defining convolutional layers. So this snippet we are going to use for the implementation of CKAN. So what it has actually, it has a number of filters, 32, kernel size 3 by 3, then stride 2 by 2, padding is equal to same, and activation function ReLU, input shape is 28 by 28, and we can give the name to the layer is a convolution layer, so conv layer. Now we are going to see CKAN architecture. As you know, we already covered convolutional layer. Now it's a time to check out the CKAN approach briefly. So CKAN is a proposed as an alternative approach to traditional multi-layer perceptron, which uses the fixed activation functions. Unlike multi-layer perceptrons, CKAN set activation function on the edges that are adaptable, and it allows the network to learn more flexible representation. And CKAN do not use linear weights. Instead, it uses a univariate functions parameterized as a spline to model relationships. So let's see the diagram first. So the first is a formula. This formula shows how a complex function can be decomposed in a series of operations, okay, by involving simpler functions. The next is a diagram B, which actually displays the structure of CKAN, where each edge you can see has a learnable activation function, and each node performs a summation of its inputs. Whereas in diagram D, it breaks down the network into three different layers, phi 1, phi 2, phi 3, where each layer processes the output of the previous layer through nonlinear learnable functions. And lastly is a CKAN of X equation. So this equation describes how an input X is transformed sequentially by three layers, with each layer applying a specific transformation and passing the result to the next. So this paper that we want to explore a little bit in this video, we are going to see its implementation for image processing. The title of the paper is called Convolutional Kolmogorov-Arnold Networks, that is CKAN approach. I have also provided the reference of the paper here. So the standard architecture that we see in CNN or MLP, they are like this. It's a CNN small, CNN medium, and one layer multi-layer perceptron. So CNN in small, first layer is input layer, then conv 2D, convolutional 2D, convolutional 2D again, then max pooling 2D layer, and then flattening layer, and then linear layer. So similar architecture you see in the CNN medium, and there is one layer multi-layer perceptron which has input layer, then linear layer, and flattening layer. These are the standard architecture. Now our target is to see convolutional CKAN architecture. Okay, so in here in the paper they have used a different architecture, 5 different architecture, and they use different data sets like MNIST and fashion MNIST data set to see the performance of each architecture. But our interest in this is this architecture, CKAN convolutional MLP2. This architecture we are also going to implement using Colab. We will see the components of this architecture one by one in detail. So first component is the input layer. So this is the layer where data enters into the network. So this is the initial layer, which is known as input layer. Then second layer and third layer is a CKAN convolutional layer. Okay, so what it has, CKAN conv comma 5 comma 3 by 3, which means these are the convolutional layer named as a CKAN conv. Each of these layer has a 5 filters or kernels, and each filter has a size of 3 by 3. As I said before, that the purpose of convolutional layer is to extract the features from the input image, and the filter slides over the image and create feature maps that indicates the presence of specific features at each place or location in the input. Then fourth layer that you see here, max pool 2D comma 2 by 2. This is the max pooling layer with a 2 by 2 filter. Pooling layer actually reduces the spatial dimensions, height and width, but not the depth of the input feature maps. Then the fifth layer is a flattening layer. So this layer flattens the 3-dimensional or 2-dimensional feature maps into one-dimensional feature map. So it is an important layer to transform from convolutional layers to fully connected layers that which processes one-dimensional data. And the last two layers are linear layers. We will see the first layer linear, 625, 256. What does it mean? It is a fully connected or dense layer with 625 inputs and 256 outputs. Fully connected layers connect every neuron in one layer to every neuron in the next layer. So which can be useful for learning non-linear combination of the features. And the last layer, which is similar like second last layer, the only difference is input and output. So linear, 256, 10. So this is additional layer which is fully connected layer. This one takes 256 inputs, the outputs of the previous linear layer, and reduces them to the 10 outputs, which means it corresponds the classification layer if this network actually designed to classify input into one of the 10 classes. So this is all about the convolutional CAN architecture. I hope you understood this architecture. The one which is highlighted, we are going to implement in the Colab. Let's see CAN convolution foundation. The major difference that I would like to highlight here is between classic and CAN convolution, that how the kernel are applied with respect to the input features. The first part A, which is kernel. This is a standard convolution filter typically used in convolutional neural network. It has a size 2 by 2 matrix with elements K11, K12, K21, K22. So this kernel slides over the input image to perform element-wise multiplication and summing them to produce output feature. I have created one in detail video on convolutional neural networks. You can check it out later. Then there is a part B, which is CAN kernel. This shows a different 2 by 2 matrix but with the elements 511, 512, 521, 522. The function appears to be similar but it's labeled differently. So in first part A is a K11 but in CAN kernel is a 511. Okay. Now next part C is image matrix. This is a representation of input image as a matrix of pixels, and these pixels are denoted by Ij. Here I represent the row and J represent the column, and the matrix size that you can see here is M by P. The next part is a classic convolution result of classic convolution. This section shows how output of classic convolution operation is computed, and the kernel moves over the image and performing element wise multiplication followed by summation of each position or each position it covers. For example, here K11 into A11. So K11 is a kernel first element and the A11 is a first element of image matrix. So multiplication of them, and then next is a summation, that is plus. The next element in the kernel matrix is K12 and next element of from image matrix is A12 and so on. That's how this operation happens in a classic convolution. So the resultant you see here in the matrix form. Here you can see phi, how it calculated. So there is a W1 into spline of X plus W2 into bias of X. And the last part is a result of CAN convolution. So here instead of taking K11, we are taking phi11 into the pixel value of image matrix. So phi11 into A11 plus phi12 into A12 on and on. That's how the convolutional operation happen in a CKAN architecture. This is a really fundamental part of the CAN convolution. So it's important when we go for the practical implementation. So next I would like to do some practical implementation where our aim is to implement convolutional CAN method, which is coming from the paper that I mentioned before. They've also provided the code in the paper, but here for the practical purpose I just use one specific architecture. In the paper they have mentioned 5 different architectures. So let's start with the demo. CAN method, first you need to create a Google Colab, and then the code that we are going to see in this video, you can implement that for your specific case study. This notebook is also available on my Git profile. You can access it from there and try to implement on your own case study, okay, for image processing. So the agenda of this video is to how to install the how to access or clone the CKAN library. Then what is CAN? We already saw it. What is CAN convolution? It is also covered in previous part of the video. Then parameter in CAN convolution, we can touch this a bit. Then result of convolutional layer with CAN. Then we can conclude, and a work in progress is from the paper. The paper link, you can access the paper from here. This is the link for the paper. So now we are going to see how to clone the CKAN. So git clone and then access the URL of the git repository, which is this one. Okay, I have this link. When you run this, it will be automatically going to clone on your system. Then next is in this library, in this directory, there are several files and directory. So you can see here architecture 28 by 28, image, CAN, convolutional, and some other files you can see. So to access that, we need to go into cd convolutional cans, the main directory name, and then there is a requirement file, which is this one. We have to install these libraries, which is matplotlib, numpy, pandas, scikit-learn, and many more. So using these commands you can do that. I already did this operation, so I'm not going to run this again. Other than that, we have to, so now we have to import the necessary libraries. So matplotlib, numpy, pandas. So these are the commonly used libraries. For the performance metrics, we are going to check precision score of the model, recall score, and F1 score. So that's why these things are important to import. Okay, then torch. These are the few things that are coming from the package from CKAN. So this is important to import. To use this to train the model, we have to import CAN convolutional layer. Then we are going to access the data. So first we are going to, the data set that we are going to access the MNIST data set. In the paper also they use this data set. Then we are loading, creating train data set and test data set using this code. And we are using data loader, and the batch size is equal to 8. This is simple. These are the few things that we need to do for the accessing the data set. And then next is the model training. So this is the code that you need to use. Even they mention, as I said before, this is the code that you have to use it. Just here we are going to see one by one. In the first half of the video, I have mentioned already that we are going to implement the CAN convolution and two-layer MLP architecture. So they in the paper there are 5 different architecture, but we picked this one. First convolution layer, using this function CAN convolution layer, we have a 5 convolution, and the size of each convolution is 3 by 3. Then second convolution layer is a 5 as well, and then size that we are passing is 3 by 3. And the next layer in the architecture is a max pooling layer. So it's a max pool TD function that are used to implement max pooling layer, and the kernel size for this layer is 2 by 2. Then next layer that we implement here is a flattening layer, and two different fully connected layers. So in first layer we have input 625 and the output will be 256, and the last fully connected layer we have 260 256 input coming from the previous layer, and the output is 10 classes. So this is a 10 classification problem, and this is the function that we are calling these layers. Okay, And the next is if we don't have a GPU, then we are setting you can use as a CPU, and here we are going to initialize the model, and we have to also define the loss function and optimizer. So the loss function that we are going to use is a cross entropy loss function, and the optimizer is a Adam optimizer. Okay. And the next is train the model for one. So these are the functions. We just wrote these functions, and now we are going to do the actual training. So for actual training, the model, the neural network model, it's important. We have to specify device, CUDA or CPU. Then we have to mention train loader, so data loader for training data. Then optimizer, so we can define HDD or other optimizer or Adam. Epochs, the current epochs, you can start from one. As per your problem, you can set the epochs. Then criteria, which means like loss function, so cross entropy you can set, and the returns that we want is the average loss over the training set. And this is where we are going to actually start the training the model. So just for the testing purpose, I just set epochs is equal to 1, and this is the training, the code for the training the model. And I'm going to call model underscore CANC dot train, and it is going to process the image as well as its label, and then it is going to give us the loss, which is the average loss over the training set. So in here the loss that we have is 0.15. The next is a model evaluation. Now we have a trained model. Now we want to evaluate it. So for evaluation, we have to set few things here. In here, we are getting the predicted classes for these batch using model. This is the model name, model underscore CANC, and we are passing images, and we are receiving output in output label. And then calculating the loss for this batch, then this is how we calculate the loss, and then calculating the accuracy for this batch, and collecting all targets and prediction for metrics calculation, normalizing test loss, then calculating accuracy and calculating overall metrics. Finally, we are going to print some performance metrics. So as I mentioned in the beginning of this notebook, that we are interested in knowing the accuracy of the model, precision of the model, recall, and F-score. So this is what, after evaluating the model or testing the model, we are getting the accuracy of 98%. I tried to implement this method. The CKAN method is in its initial phase, so there is no lot of development we see out there, but we can try for our case study for sure. This is the research that I found interesting because it's a new thing that I see in machine learning. But let me know your thoughts in the comment, and thanks for watching the video. I hope you like this video. Please subscribe to the channel, like the video, share this video with your friends, those who are interested in learning machine learning approaches. And if you have any questions, doubt related to this video, please let me know in the comment. And thanks for watching the video, and see you in the next video.